All right, how's it going, everybody? So this video I'll be talking about place value and other number systems. And so one of my students, Alex, requested that after I ask how's it going in a video, that I pause so that he has enough time to um, give an answer. So I'm gonna pause now. So Alex, go ahead and let us know how you're doing. Okay. Uh-huh. Okay, so I'm going to assume Alex is done letting us know, or maybe he's continuing to scream into the void there. But great. Let's look at the learning targets for today. Um, Number one, we're going to look at negative exponents. So kind of where they came from and why mathematicians decided to um, sort of have make why they decided to make them work the way they do. We'll see they fit into a very simple pattern. So you might have seen this before, but I'm just going to review that. Um, then we're going to kind of take it back to elementary school. We're going to look at place value and connect it to exponential patterns. So we've looked at some other uses of exponential patterns. In this video, we'll talk about how exponential patterns can be used to represent numbers. And in particular, we'll learn about other number systems. So using what are called different bases for number systems. So you'll be able to write, so one of the main goals there is that third one, be able to write down any number in any base as a sum of powers. Okay, and we'll see what that means here. But let's start with negative exponents. So suppose you wanted to know what is 3 raised to the negative second power. And again, what I'm about to say is true as long as we have whole number exponents. And we'll deal with fractional exponents later. But for now, what is 3 to the negative 2? So, mathematicians had a choice. They had to kind of decide, like, what should this thing mean? And if we look, we'll see it fits very nicely into a pattern, right? So with positive exponents, with whole numbers anyway, 3 to the first is 3, 3 squared is 9, 3 cubed is 27, and it's because it means repeatedly multiply, right? The exponent tells you how many times you're going to multiply by 3. To get from 3 to 9, I multiply by 3, so that's 3 times 3 is 9. To get from 9 to 27, I multiply by 3 again. And then you ask yourself, well, okay, what's the sensible, logical thing to put over here on the left? Well, if going out to the right with positive exponents, I'm multiplying by 3, then how can I get to the left? Well, just run the pattern in reverse. And what's going to undo, what's the reverse of multiplying by 3? It's dividing by 3, right? So, to get from 27 to 9, I divide by 3. To get from 9 to 3, I divide by 3. And then what's going to go here? Well, I divide by 3 again. So what ought to be 3 to the 0? It's 3 over 3, or 1, right? And I can keep running this thing out as far as I want. 1 divided by 3 is a third, and if you take a third and divide that into 3, you get a ninth, right? Taking a third of a third is taking a ninth. If you cut a pizza in 3 and then you cut those 3's into 3's, you have 9 pieces, or 1/9, right? So what I'd like you to notice here is that there's really nice parity, right? So this pattern is perfectly symmetric if I look on either side of the 1, right? So 3 to the 0 is 1. If I look at 3 to the first, it's 3. And if I look at 3 to the minus 1, it's 1 over 3, right? If I look at 3 to the second power, it's 9. If I look at 3 to the negative second power, it's 1 over 9. So there's this nice parity, this nice symmetry that goes on that keeps this pattern nice and consistent, right? Mathematicians could have decided to put anything here, right? So mathematicians make the rules, right? But they decided I clicked the button there. They decided the most logical thing to do here was to make this a nice symmetric pattern. Okay, so to summarize, if a positive whole number exponent means repeatedly multiply, then a negative whole number exponent means repeatedly divide, right? It's just keeping that symmetry. Now, in a textbook or in a previous class, you might have learned like something a teacher might have called a flip rule, or the textbook might call the flip rule, which is just to say that like if you have 3 to the negative second power, then you can like flip it to the bottom of the fraction and make it a positive. And it's fine if you know this rule already and are comfortable with it, but I would encourage you to think back to that pattern, because that really explains why this is the case. Remember, if the positive 2 exponent means multiply, the negative 2 exponent is going to mean divide by 3 2 times, right? So you get 1/9. in general, if you have any number raised to the negative whatever, a to the negative b, you can rewrite that as 1 over a to the b to make sense of it. That's what, in a sense, that's what it means, right? Okay, but so I would encourage you to look at the pattern for understanding and not memorize the rule. Now here's the thing. Now we're going to move into like, okay, how can we use these exponential patterns and our understanding of negative exponents now to represent numbers? So our entire system of counting is based off of the exponential pattern with base 10. Okay? And this is where I mentioned this is like going back to elementary school. The powers of 10 are what your elementary school teacher called the place values, right? And it really is as simple as elementary school, except now we have a slightly more sophisticated way to represent the information, right? So in elementary school, you talk about the ones place, the tens place, the hundreds place, and now I'm just saying, look, we're going to rewrite this using exponential notation. And there's a reason that we'll do it, that. We'll see why in a minute. But it'll make things more consistent and more clear. But we'll get there in a second. But for now, like, yeah, this is literally just place value. Notice now the tenths place is 10 to the minus 1 as a power of 10, or 1 over 10. 10 to the minus 2 is the hundredths place, or 1 over 100. And the thousandths place, 1 over 1,000. But again, keep in mind this nice, pretty symmetry, right? 10 to the first is 10, 10 to the minus 1 is 1 over 10, okay? And I've noticed students tend to gravitate more towards decimals, so here I've written it with decimals, although I will point out that the only ugly thing about the decimals is you kind of lose your nice symmetry. But 1 over 10 is 0.1, 1 over 100 is 0.01. It doesn't really matter. You should be able to use either a representation, a fraction, or a decimal. I do like the fractions because you get that nice symmetry. The 100, 10 squared, the 1 over 100, 10 to the minus 2, right? You sort of lose the symmetry there. It's kind of like off by a 0, if you see what I mean. The 100.01 versus 100. The 100 has one extra 0 when written as a decimal. But anyway, the whole point here, you can rewrite any number as a sum of powers of 10. That's the more sophisticated way to write it now that we're not in elementary school. In elementary school, you would have said 546 is broken up into 5 100s, 4 10s, and 6 1s, and now I'm saying let's write that as powers of 10. So yes, it is 500 plus 40 plus 6 broken up into the place values, but we can write that as 5 times 10 squared, there's your hundreds, plus 4 times 10 to the first, plus 6 times 10 to the 0. Okay. You can do the same with decimals. If I wrote 46.32 as a sum of powers of 10s, I would get 4 times 10 to the first plus 6 times 10 to the 0. That's 4 10s, 6 1s, 3 tenths, 10 to the minus 1, and 2 hundredths, 10 to the minus 2. Again, those last ones, this is 3 over 10 and 2 over 100 because, again, the negative exponent means divide. So 3 times 10 to the minus 1 is 3 divided by 10. 2 times 10 to the minus 2 is 2 divided by 100. Okay? But either way, you should be able to connect like what you did in elementary school versus how exponential patterns fit into this representation of numbers. Okay, so why did people decide to count by powers of 10? It's actually kind of a somewhat arbitrary choice. It's because we happen to have 10 fingers, right? That's why everything is base 10. That's why we use the exponential pattern with tens. It's because we have 10 fingers to count with, right? And also I'll just point out here, our system of counting is called the base 10 system, or sometimes it's called the decimal system. DEC is the root word for dec stands for 10, right? And to write any whole number, you only need 10 characters. You need a 0, a 1, a 2, and so on to a 9, right? Because once I have to write 10, I just use the 1 and the 0 again. Or if I have to write 102, it's not really a new thing. I just take the 1, the 0, and the 2, and I combine them all together. That's why when you look on a calculator, there's only 10 buttons, 0 through 9, right? But yeah, so we'll see why this is relevant in a second. But the whole point here is, we started counting in base 10 really because we have 10 fingers to count on. And so that's how things kind of got started. But it turns out that if we change 10, so imagine if instead of having 10 fingers, we had like 12 fingers or 4 fingers or 6 fingers, things might have been a little different. And it turns out these other different systems are actually useful. So by just changing the 10 to a different number, you get a whole new way to represent numbers. And here's the most well-known is binary, right? So you've probably seen binary like in movies or, on TV or whatever, where it's like a computer and there's like lots of ones and zeros. And some of people have some understanding that computers use ones and zeros, but I would guess most people don't really understand why that's the case. And we're going to talk about why that's the case. So, okay, so as long as you can count with base 10, you'll find that you can also count with base 2, which is what computers use. So let's start with just the mathematics of it, and then I'll explain kind of why computers use binary. Okay, well, just like you had a place values in base 10, just use the exponential pattern for base 2. So what does the pattern look like in base 2s? Well, it's basically the same thing, except you have 2s instead of 10s, right? So 2 to the 0 is still 1, 2 to the first is 2, 2 squared is 4, and 2 cubed is 8. That means in base 2, instead of having a tens place, a hundredths place, a thousandths place, you have an eights place, you have a fours place, you have a twos place, a ones place, and then the decimals, instead of saying tenths, hundredths, thousands, you have halves, 1 over 2, quarters, 1 over 4, and eighths, 1 over 8, right? That's 2 to the minus 3 is 1 over 8. 2 to the minus 2 is 1 over 4. 2 to the minus 1 is 1 half, right? Again, there's this nice, pretty symmetry between the positive exponents and the negative exponents. 4 and 1 over 4, 8 and 1 over 8. Okay, but what we're going to do here is we're going to use these as our place values. Instead of base 10, we're going to use base 2. So it's like imagining, as I said before, it's imagining we don't have 10 fingers, we just have 2 fingers. So now we're going to use the symbols 0 and 1. Those are our 2 fingers, finger 0 and finger 1, right? All right, so let's look at some examples. It looks funny when you first learn this. So what does 101 represent in base 2? So you're like, well, that's the number 101, but you have to turn your mind off of thinking base 10. You're so programmed to do it, it's going to be hard. But I promise when we write it down, it'll make perfect sense. What does 101 represent in base 2? Well, again, now we're using different place values. So if I look at my exponential pattern, 2 to the 0, 2 to the first, 2 to the second, well, that's my 1's place, my 2's place, and my 4's place. So what does 101 mean in binary? It means you take 1 4, you take 0 2's, and 1 1, which gives us our normal decimal number, our base 10 number of 5, because 1 4 plus 1 1 is 5, right? So written a slightly different way here, same thing though, 101 in base 2, that means you take 1 as a sum of powers, it's 1 times 2 squared, plus 0 times 2 to the first, that's my next place value, my 2's place value, plus 1 times 2 to the 0, that's my 1's place value. Or if we write it out in our normal standard decimal notation, that becomes 1 4, 0 2's, and 1 1, or 4 plus 1 is 5 in base 10. So it's kind of a funny thing when you first see it. It's like saying 101, that number is the same as the number 5 over here. But again, it's because the way we're representing the number is different, right? In binary, we're representing using powers of 2's, and in decimals, it's powers of 10's, right? Decimal, we also have 10 fingers to count with, so we can count to 5. Binary, we only have 0's and 1's to count with. All right, let's do a couple more examples. How do you write the number 9 in binary? So the decimal number 9, when you have 9 fingers, how do I write that in binary using 0's and 1's? Okay, well, I claim that 9 in base 10 is 1001 in base 2. Now would be a good place to pause the video to try to work this out on your own. Okay, but I'll go through it here together. So 1001, again, ask yourself, well, what place values are being represented? Again, since we're base 2, we're using this exponential pattern. We have the 8's place, the 4's place, the 2's place, and the 1's place. And so this is saying take 1 8, 0 4's, 0 2's, and 1 1. And of course, 1 8 and 1 1 gives you a 9 in our decimal counting system. Yeah, so that's all I got to say there. If you had to write it as a sum of powers, you would write it as 1 times 2 cubed plus 1 times 2 to the 0. How do you write the number 4.75 in binary? Okay, so now I have a decimal, but really nothing's going to change. You just have to use those place values. And remember that in base 2, our decimal spots are the halves place, the quarters place, and the eighths place, right? So 4.75, if I write it all down, it's 1 4, that's my 4. Since I have a fours place, I can take a 4 in binary. It's 1/2. I have a half. I have a halves place there. And 1/4. I have a quarters place. Because a half plus a quarter is 0.75 or 3/4, I can represent it like this. Take 1 4. There's my 4. I don't need any 2's. I don't need any 1's. So that's why these are both 0's. And then I put my decimals point, right? And now I take 1/2 and 1/4, right? So writing it all down here, base 10, 4.75 looks like 100.11 in binary. And again, it's just looking at each place value. There's the 4's place value where there's a 1, there's no 2's, no 1's. There is 1 1/2, and there is 1 1/4, because a half plus a quarter is 3/4 or 0.75. Okay, and to kind of conclude this, why is binary important in computing? Why do you hear about this? Why is this something that shows up in movies like The Matrix or whatever? Computers use binary because the little computer chips that power your CPU, they have these tiny little switches on them. They're like little electronic switches, really. And they're called transistors. And every computer chip nowadays has billions of these things. So billions of tiny little switches are on the chip inside of your computer. And when you have a switch, how you encode information is your switch is either on or it's off. And this is where the 0 and the 1 come from. If the switch is on, it's a 1. If the switch is off, it's a 0. So the actual physical hardware in the computer is built of these little transistors, these little switches. And so to represent numbers then, the switches are either on, 1, or off, 0. And that's why all the data in the computer, all the information on your computer gets stored as these strings of 0's and 1's. And that's why binary is kind of the like low-level representation of numbers. That's why binary gets used when representing information in computers. Okay, there's many other examples of other number systems that are useful. Binary is just the most sort of popular one. So to kind of tie it all together here and wrap up, base 10, when you're using those powers of 10s for the place values, is our normal usual counting system. Base 2 is called binary, but if you change the number that generates the exponential pattern, right, instead of saying 2's, 4's, 8's, 16's, what if you did 3's, 9's, 27's, 81's, etc.? You can get other number systems that might be used to represent other types of information more naturally. And I've sort of summarized it up here. Base 10, we have 10 fingers, so that's why we have 10 symbols. And here are our place values, the thousands place, the hundreds place, the tens, the ones, the 1/10ths, and so on. Base 2 is like 2 fingers. You get a 0 and a 1 finger. And your place values are 8s, 4s, 2s, 1s, halves, 4s, 8s. But of course you could do the same thing. Base 3, now you have 3 fingers, 0, 1, 2. And these are your place values, right? Notice the nice symmetry. Base 4, you have 4 fingers, so the symbols 0, 1, 2, and 3, and these are your place values. Of course, this goes on. Any number you want to put in there could be a base. I think if you know a little bit of representing colors in computers, like hexadecimal is like base 16. So base 16 is used a lot too to represent color in computer programming languages. Maybe you've seen that one. If not, that's okay too. So I'll wrap up this video, just a little summary. So negative exponents, you should be able to understand sort of why they were described as they were, how it fits into that little pattern, right? If a positive exponent means repeatedly multiply, a negative ought to mean repeatedly divide, at least for whole numbers. We recapped like elementary school stuff about place value, except we wrote it a little more sophisticated. So you can write now any number as powers of 10s in each place value. And of course we use the symbols 0 through 9. And we talked about other number systems. In particular, we looked at binary. Binary uses powers of 2s for the place value and the characters 0 and 1. But, it could be base 3 or base 4, whatever base you want. Okay, so thanks for listening and have a good one.